Hi everyone. Today I'm going to talk about visualizing probability distributions across bivariate cyclic temporal granularities. My name is Sayani Gupta and I'm currently doing my PhD at Monash University. If you would like to follow along my slides, you can find them at sayanigupta-ows2020.netlify.app. You can follow me on GitHub at Sayani07 and on Twitter at SayaniGupta07. This is a joint work with my thesis supervisors, Professor Rob Heinemann and Professor Diane Cook. So I'll talk briefly about the motivation of this problem. Smart meters are devices that digitally measures our energy usage. They are now in place in all homes in Victoria, which means every year, data for 6.4 million households are recorded for every 30 minutes of an hour, for every 24 hours of the day, and for every 365 days of the year, which in turn implies that there are more than 100 billion half-hourly observations that are collected per year for just one state, Victoria. These households have different demographic properties such as existence of solar panels, central heating, air conditioning, as well as different behavioral patterns. In this display, I plot the energy consumption along the y-axis against time from past to future. As can be observed from the animation, energy consumption in households vary substantially, which is a reflection of their varied behaviors. If we plot the raw data for all of them together, it is very difficult, if not impossible, to get useful insights of their behavior. The motivation of my work comes from the desire to provide methods to better understand these kinds of large temporal data sets that are observed more than once per year. My research proposes that deconstructing a time index into time granularities can assist in exploration of periodicity and automated analysis of large temporal data sets. There could be different classes of time deconstructions. Linear time granularities respect the linear progression of time, like hours, days, weeks, and generally represented through a line plot going from past to future. Cyclic granularities, like hour of the day or day of the week, could be used to explore periodicities in the data. These granularities can be considered as categorical variable, which could be ordered or unordered, and they induce a grouping of this observation. So as you can see from the animation here, that when we move from a linear to a cyclic world, we have a scenario where we have multiple observations for each category. Hence, there is a need to summarize them. There are several possibilities at our disposal for visualizing statistical distribution. Traditional methods of plotting include box plot, violin plot, ridge plots, whereas more recent forms of visualizing distribution include letter values, quantiles, or highest density region plots. Talking about the data structure that we want to consider for visualization, Sybil is a temporal data structure that consists of index, key, and measured variable. An index is a variable with inherent ordering from past to present, and a key is a set of variables that define observational units over time. In a Sybil, each observation is uniquely identified by the index and the key. Since any cyclic granularities are function of the index variable here, we can extend the Sybil data structure to include all the cyclic granularities. Now, why are we interested to look at a lot of cyclic granularities? Because they would help us to look at the data from multiple perspectives. More than two cyclic granularities could be looked at the same time, but we decided to look at only two cyclic granularities at the same time. So we considered Ci and Cj, where Ci maps to categories A1, A2, AK, and Cj maps to categories B1, B2, BL. For relating the data space to the graphic space through layered grammar of graphics, we map Ci to the facets, Cj to the x-axis, and the numeric response variable on the y-axis. Now suppose we have NC cyclic granularities that we would want to consider for our analysis. Then taking two of them at a time and placing one of them on the x-axis and the other one on facet, we can have a total of NC permutation 2 displays that we have to uncover. Now the number of displays that are there even for small NC become too large too soon. For example, even for 10 cyclic granularities, we will have 10 permutation 2, which is 90 displays to look at and analyze. Without a systematic approach, it is difficult for an analyst to do that. So we will essentially try to scrape some displays and keep only those displays which could be interesting. For starters, not all pairs of cyclic granularities are compatible with each other for exploration. Take the first one as an example. Here the facets are month of the year and the x-axis show day of the year. We are unable to compare the distribution across facets because many of their combinations are missing. This is also intuitive because the first day of the month can never be second or third day of the year. These pairs which lead to structurally empty combinations are called clashes. The pairs that are compatible with each other are called harmonies. For the second plot, every day of the week will be there for every month of the year, which means there will be no missing combinations, and these are the pairs of cyclic granularities that could be looked together for exploration. Still, for large NC, which is the number of cyclic granularities that we have considered for our analysis, we could have possibly many harmonies. Now we ask the questions if we can rank the harmonies in order of the importance, and if we can also remove some harmonies from the list for which variations in the response variable is not significant enough. So what do I mean by that? Look at both of these graphs that display harmonies. Clearly, B captures more variation of the response variable than A. Gestalt theory suggests that when items are placed in close proximity, people assume that they are in the same group because they are close to one another and apart from other groups. Hence, given our data structure, displays that capture more variation within different categories in the same group would deem to be important to our eyes. Hence, the idea here is to efficiently compute a statistical measure that capture the within group and between group variation and remove all harmony pairs for which variation is not significant enough. Also, we should rank a harmony pair higher if the variation between different levels of the x-axis variable is higher on the average. Here you can see that the variation across different category of the x-axis is higher for B than for A, and hence B should be ranked higher. The measure we obtain is called median maximum pairwise distances, MMPD, which uses Jensen-Shannon divergences for measuring distance between distribution and uses the Fisher-Trippett theorem for normalizing for the number of categories. All the ideas presented have been implemented in the open source R package Gravitas. I will post the links at the end. Through the package, we provide methods to create possible granularities for a time index, determine feasibility of examining them together called harmony or clash, refining the exploration by looking only at significantly different pairs, and recommending appropriate distribution display. We will see an example of a sample data from Smart Grid Smart City project from Department of Environment and Energy, Australia. It has the columns customer ID, which serves as the key, the reading date time, which is the index of the civil, and general supply kWh, which is the energy consumption measured in kilowatt hour, is the measured variable. So suppose we start with 7 cyclic granularities, which are hour day, hour of the week, hour of the month, day of the week, day of the month, week of the month, weekend, weekday. Then we will have 7 permutation 2, which is 42 pairs of granularities, that is 42 displays to look at to have an exhaustive view about the data. When we use the concept of harmonies and clashes, directly from 42 displays, we are left with only 16 displays, which could be visualized in order to derive any insights. We further reduce it to 6 by choosing harmonies whose MMPD are above a significant threshold. Now, 6 displays are much easier to analyze than 42, right? So we have been able to screen and reduce and refine our search to have only 6 displays, which will help us to analyze the periodicities of the entire data. Thank you for listening. Please visit the GitHub repository for more information on this work. Thank you so much.